Otherwise, without further ado, we are very happy to have Nima Arkani-Hamed this week. And Nima will be giving a talk on space-time quantum mechanics and clusterhedra at infinity. Nima, can you share your screen?
All right, let me see. Hold on 1 second. Let's just do that. Is everything okay?
Yep.
Okay, great. I'm really delighted to be able to give this talk. Thanks a lot to Tudor for the invitation. And I'm talking about broadly a line of work that stretches back a decade with a large number of collaborators, both physicists and mathematicians. But a particular point of view on these developments has sort of emerged in the last 2.5 years or so, which I'll mostly be emphasizing. And the most recent work on sort of defining what these clusterhedron objects are in most relevant generality is work very much in progress with the underlying names here, Hugh Thomas and Pierre-Guy Plamondon, who are mathematicians, and some wonderful young physics collaborators, Giulio Salvatore and Hadley Frost. So let me begin with some. Sorry, I'm having difficulty. Okay, let me begin with some highfalutin and also then more practical motivations for this general line of investigation. We've gotten very used over the last 20 years to the idea that when we have quantum mechanics and gravity, the only observables we're allowed to talk about live on the boundaries of space-time, and especially in the context of gauge-gravity duality in anti-de Sitter space. We've gotten used to the idea that the observables live on this on the boundary of anti-de Sitter space, and there's an ordinary quantum mechanical theory there that calculates those observations that start and end on the walls of the anti-de Sitter space. So, in a precise sense, the quantum mechanics of the boundary theory gives rise holographically to the interior in a way that's still being understood and being developed, of course. Now, one thing this doesn't let us do is understand the origin of time, and this is a crucial part of the duality. The time that flows on the boundary is the same as the time in the interior, and so this is really an example not of space-time emerging from more primitive building blocks, but of space emerging from an underlying quantum mechanical system, which is otherwise an ordinary quantum mechanical system with an ordinary notion of evolution in time. As we get closer to describing the real world, one significant step closer to describing the real world is to talk about observables in flat space-time. And here, the analog of the boundary of observables are scattering amplitudes, which are scattering processes, which are also happen to be the experimental sort of bread and butter of high-energy fundamental physics. Moving on to cosmology, the observables that we would talk about are just measurements that are made in infinite late time in a cosmological universe. And in both of these cases, things are fundamentally more mysterious than in anti-de Sitter space, because every way of thinking about what the boundary of these more realistic spacetimes look like don't have an obvious notion of time or of locality. And so if you're going to pursue this sort of holographic strategy for these spacetimes that are closer to the real world, one has to necessarily be more adventurous. And we'll have an idea, we'll have some picture of what that little bit more adventurous looks like in this talk. And instead of quantum mechanics being king and having space emerge from it, now this is very speculative, but we're getting increasing amounts of evidence that there are some other kinds of questions and ideas and structures, and quantum mechanics and space-time will be seen to emerge from them hand in hand. So if we talk about the question about scattering amplitudes, imagine that you're an experimentalist at infinity. You just throw particles into the middle of the space-time, they bang into each other and they come back out. The observation is made at the beginning and end of space-time, it's made at the boundary of space-time, but something happens inside to give rise to the scattering process. And we can ask, what is the question to which this scattering amplitude is the answer? And of course, the conventional question is local evolution in space-time. We draw pictures of Feynman diagrams, particles propagating in, bang into each other at local points in space-time, reflecting some underlying unitary evolution in Hilbert space. So it's locality in space-time and unitary evolution in Hilbert space, which is what's responsible for the scattering process. And in fact, locality and unitarity, loosely, trying to understand this precisely is an ongoing challenge, but loosely, locality and unitarity are encoded in a certain analytic properties of the scattering amplitude, something universal about their singularities. That's the imprint of what locality and unitarity is. And you can actually think that local unitary evolution in space-time is something that we add from the outside in order to make these singularity structures of the amplitudes manifest. What we've been doing over the past decade is reversing this question. We want to see the amplitudes of the answer to a different question and understand from this different question how the rules of space-time and quantum mechanics, locality and unitarity, come out as derivative outputs. So there's some other structure that's going to let us see, amongst other things, that these objects that we're going to call amplitudes have these very special kinds of singularity and factorization properties that we can then infer as being associated with the existence of an underlying local space-time unitary Hilbert space description. We'll see precise examples of that in this talk. Now, that was a highfalutin set of motivations. A much more practical set of motivations is that people actually have to calculate these scattering amplitudes for a living, for example, in order to make predictions that experimentalists can measure at the Large Hadron Collider, have found over the last 30 years that the conventional way of thinking about this physics that we learn in the textbooks that goes back to Feynman and Feynman diagrams, this conventional way, which even in the simplest case, let's say, here's the process relevant at the LHC, 2 gluons in, 4 gluons out. The gluons turn into jets of strongly interacting particles. But anyway, this is a process that happens hundreds of thousands of times a second in proton-proton collisions at the LHC. And if you open up your quantum field theory textbook and start trying to do this calculation, you're just supposed to draw all these pictures. And there's a combinatorial explosion in the number of ways these processes could happen. And if you actually put them all together, you get tens of thousands of terms. Here's a picture of what you get from a direct brute force calculation, even for 2 to 3 scattering. It's not even 2 to 4. It's about 100 horrible pages of algebra that look like that. But 30 years ago, a little over 30 years ago, people discovered that in many cases, the result of these hundreds of pages of algebra collapsed to a single line. And back then, it was not clear that it was the tip of a giant iceberg. Today, we know it's a tip of a giant iceberg. This is already an indication of the standard way of doing the physics that makes the usual rules of space-time and quantum mechanics manifest, is obviously hiding some other extraordinary structures. And so part of the goal of this whole program is to understand a different starting point, a different question to which these amplitudes are the answer, which will make the simplicity manifest and certain hidden infinite dimensional symmetries, some of which we'll talk about, manifest. But space-time and quantum mechanics will not be the stars of the show anymore. If we make locality and unitarity manifest, that's the purpose in life of Feynman diagrams, but it's clearly hiding something. The goal here is to find a different question to which the amplitudes are the answer, and then to be able to read out how it ends up having an interpretation in terms of local space-time unitary Hilbert space physics. Okay, so saying it yet again, for the past 10 years or so, we've been trying to fill in that question mark with something else, and the something else ends up involving, in the examples that we've seen so far, these notions of positive geometries in kinematic space, which is the space where the amplitudes actually live. Kinematic space is one way or another ways of labeling the physical on-shell momenta of the particles participating in the scattering process. No virtual particles, just the data that makes it out to infinity that specifies what the actual scattering process is. And so again, the question is, we have a canvas which is given either in terms of many ways of labeling how things make it out to the boundaries of Minkowski space, either the null momenta of the particles, or twistor variables, or coordinates on the celestial sphere. These are many different ways of talking about the sort of kinematic data of the particles that make it out to infinity. And in these seemingly arid, dry spaces with not much going on, the space is the space of n null momenta or n twistor variables. That's it. There's no notion of locality. There's no notion of time. There's no standard physical notions that we're used to that we can sort of put on this boundary space. But somehow we have to find some ideas or some kind of mathematical question that breathes physics life into the seemingly arid space. And again, the emerging picture over the last 10 years is that there are some essentially combinatorial ideas in kinematic space that are associated with these notions of positive geometries, and analytic ideas, certain canonical differential forms that are associated with these geometries. And we'll be going through an especially simple example of this story today. The sort of first instantiation of these ideas was in the context of n equals 4 super Yang-Mills amplitudes and the story of the amplituhedron. I'll be talking about completely non-supersymmetric theories today. So just the phi cube theories with some color indices, where these positive geometries are actually much simpler objects. They're polytopes, generalized associahedra, and they with some interesting relationship to cluster algebras and leading to this notion of clusterhedra that we'll talk about in this talk. But just at this point, I just want to emphasize that these ideas are not some esoteric that's only tangentially related to the real world. These things describe real world physics in a reasonable approximation, and the world's out there outside your window. Along the way, expose hidden symmetries and new mathematical structures. To me, the most remarkable aspect of this subject is how much pure magic is sitting there right in physics under our noses. Physics we know describes the world, but which we haven't looked at from this through this lens before. Okay, so let me just give a couple of slides on what this idea of positive geometries is, because mostly we'll be focusing on what the geometries look like in kinematic space. But I want to describe roughly how this idea of the geometries ends up determining a function like a scattering amplitude, an interesting function that depends on kinematical data and so on. A positive geometry loosely, it's possible to give a more precise definition, but loosely is some region P that has boundaries of all possible codimensions. So some real compact region in a real geometry. The simplest example would be like the inside of an interval, or the inside of a triangle, or the inside of polytopes in general. But there are sort of curvier generalizations of them in grassmannians and so on, which ironically, the more sophisticated versions of these ideas were the first ones that were run into in the context of maximally supersymmetric scattering amplitudes. But you can, that's why I've drawn this picture kind of curvy, but the sort of simplest version is just the inside of polygons or polytopes in higher dimensions. So that's a geometry, but associated with it is a certain differential form. And what determines this differential form is that it's a unique differential form with the property that it has logarithmic singularities on and only on all the boundaries of this space. So logarithmic singularities means that locally there's a set of coordinates where the form looks like the wedge product of a bunch of d logs, dx1 over x1 up to dxd over xd. So that's the way in which a certain real geometry is associated with this analytic object, the differential form. The form is sort of a slave to the geometry. And so what we're going to do is see these positive geometries naturally arising in the kinematic space that defines the scattering processes. And this canonical form will then give us the corresponding physical object. And I'll be more precise about how we get the corresponding physical object like the scattering amplitude out of this canonical form. So here are some very simple examples. The simplest example of the canonical form is the inside of an interval. And so here, the canonical form that has logarithmic singularities on and only on the boundaries of this interval is a dx over x minus a minus dx over x minus b. And the minus sign is important. If we had a plus sign, this form would also have a logarithmic singularity at infinity. So we only wanted to have logarithmic singularities on and only on the boundaries of the space, which is the origin of that minus sign. Similarly, if I talk about the inside of a triangle, this triangle, the canonical form, just has poles where you'd expect on the boundaries of the space. And very nicely, if you further take a residue, let's say on x equals 0 to end up on that line, then the resulting canonical form is just that of the interval that you see on the line. So that's the point, that the canonical form has singularities, logarithmic singularities on and only on the boundaries of the space. Already for very simple examples, like a quadrilateral or a pentagon or a polygon in 2 dimensions more generally, the canonical form is more interesting because just looking at what the possible poles are does not completely fix it. And they have to have interesting numerators that guarantee that the singularities happen only on the boundaries of the space. So, but the general lesson is that the singularities of the canonical form reflect the boundary facet structure of the positive geometry. And finally, if you want to actually compute these canonical forms, there are many ways of doing it. But one natural way is by triangulation. So if someone hands you a more complicated positive geometry like this hexagon, then you can break it up into simpler pieces, into triangles, and we know what the canonical forms for each piece are, and very slightly non-trivially, the canonical form for the whole thing is simply the sum over the canonical forms of the pieces. Each term will have some spurious poles corresponding to these internal boundaries, but the spurious poles necessarily cancel in the sum. One particular example is a sort of universal way of triangulating any polytope, which is simple. A simple polytope is one that locally in the neighborhood of every vertex looks like a simplex. And this corresponds to a kind of inclusion-exclusion type triangulation of the polytope. For example, if I want to triangulate this square, I can draw a line at infinity and from every vertex continue the edges until they meet infinity. So this gives me the sum of a bunch of triangles, which by inclusion exclusion gives me the quadrilateral itself. You'll see why I'm going through this example in a second. This is going to end up being the origin of Feynman diagrams when we ultimately get there. Okay, so, but anyway, this is an example of one particular triangulation, and you'll notice this is a triangulation which every term has this spurious pole at infinity that only cancels in the sum. Okay, now I'm going to turn to the actual theory that we're going to be talking about. That's this bi-adjoint phi cube theory. So this is just a scalar theory with a cubic interaction, and we want this scalar to have a color. But if we just had phi A, phi B, phi C, and we multiply by FABC, we'd get 0. So we give it two colors. That's why it's called bi-adjoint. We have an F little ABC and an F big ABC. Okay, but apart from this, this is just an excuse to write down sums of planar diagrams, more generally diagrams that we can draw on genus G Riemann surfaces. As we're used to from Yang-Mills theory, there's a trace decomposition for these amplitudes, but now because we have two colors, we have two sets of traces, one for color little a and one for color big A. So we can have single trace terms that has just one of each, double trace terms that has two of each, and so on. We have also the usual 1/n or genus expansion, where now the diagrams have to be consistent with orderings for both the little a and the big A orderings. So what we're going to do from now on is focus on the case where the two orderings are the same, in which case the diagrammatics are just identical to ordinary one color Yang-Mills theory, but we just have, but we don't have any polarizations or anything more complicated. We just have a simple scalar theory. So this is what things look like at tree level. At tree level, I would label, I didn't do it here, but I'd label all the indices 1 through n, and we just sum over all the cubic diagrams consistent with that order. So that's what we do. That's what Feynman diagrams would tell us to do. We can dually describe this by just drawing the dual of the Feynman diagram. This is going to be a very useful idea. If we draw the dual of the Feynman diagram, what we get is a triangulation of this hexagon. So I have 6 external particles. The dual of this cubic diagram is simply a triangulation of the hexagon. This polygon that we get here is actually very natural. Since we do have an ordering on the outside, we can just imagine drawing all the momenta, P1, P2 up to Pn, and momentum conservation just tells us that they form the vertices of a closed polygon. Each edge here is a momentum. So momentum conservation just tells us sum of all these vectors adds up to 0. And a very convenient basis for all of the Lorentz invariant, Mandelstam invariants that we can talk about is actually given by all of the distances squared in this polygon, which corresponds to the sum of consecutive momenta squared. So this variable xij you see here is the same as xji. We're going to be dealing with massless particle scattering, so xii plus 1. Each one of these no momenta squares to 0. So these are our variables. Our variables are xij. That's it. That's our kinematic space. So we're going to be coming back to this, but the space in which the amplitudes live are just the function of these dumb xij, where xi plus 1 is 0. But if we just continue with how we think about the amplitudes, these tree amplitudes in the usual way, we can think of it as sum over all Feynman diagrams. Equivalently, we can think about it as the sum over all the triangulations of the polygon times the product over all the chords in the triangulation of 1 over the xij. So that's what's inside the box. That's in the conventional picture of what's inside the question mark for scattering amplitude. This is what's going on. Okay, now there are a few very simple and important facts are how locality and unitarity, even at tree level, are reflected in this picture. Locality is reflected in the fact that the poles that are allowed are precisely those that don't cross. So this is a triangulation. This shows up in a Feynman diagram. This is allowed. But something with the chords crossing is not allowed, and that's basically the physics of locality. For 4-particle scattering, it says that we can have a pole in the S channel or the T channel, but not both at the same time. So the fact that we can't have crossing chords is the physics of locality. What's unitarity? Unitarity tells us that there has to be a pole as one of these variables goes to 0. So as xij goes to 0, we have to have a pole that would correspond to the virtual particle that's dual to this line going on shell. So there's a pole there, and the residue of that pole factorizes into the product of the 2 smaller amplitudes on the left and on the right. So locality says which pattern of poles are allowed to come together, and unitarity says what happens on the poles, the amplitude has to factorize into the product of 2 smaller amplitudes. Okay, so that's the conventional picture for what's going on. Now let's back up and imagine we didn't know that. And imagine that we're instead just some experimentalist who lives at infinity, who has their finger on the dial of the Mandelstam invariance and is moving things around in order to see what's going on, what's giving rise to these interesting functions that they're measuring. And the first thing the experimentalist would notice, any experimentalist would notice, is that these amplitudes blow up somewhere. They have poles. And that if they're very careful and did very detailed measurements, the first kind of experimentalist who would study this, who's really a closet theorist, would do some detailed measurements in the neighborhood of the pole and discover, wow, it factorizes on the poles. Amazing. And they announce this at a conference, and there are 2 kinds of theorists in the audience. One of them is called Feynman. And from that clue, they say, oh, I know what's going on. It's Feynman diagrams that I just named after me. And they're just the sum of all these diagrams of these virtual particles in the middle, and that guarantees this picture. Another theorist is sitting in the audience, maybe his name is Deline, and says, oh, no, I've seen this before. This is just what happens for the simplest moduli space of n points on the boundary of a disk, that on the boundaries factors into this bubbling picture of the product of 2 smaller spaces of the same type. And this is a second sort of simple mathematical structure that manifests this factorizing property. And that gives us, that's the beginning of the picture of the string world sheet as responsible for what's going on. So I'm emphasizing that when just factorization is the star of the show, that gives us our 2 pictures that we've had for 50 years for what the underlying physics of particle scattering is. It's either particles in space-time or the string world sheet. So is there anything else left to be desired? Anything else left to understand? Well, there's actually a bigger clue. The hero of my story here is a laser experimentalist who does a different kind of observation. They notice that they don't do any detailed measurements of what's happening around every pole. They just notice that only certain patterns of poles come together. For instance, they're excited by the fact that the amplitude blows up, so then they move the variables around and try to make it blow up more. 1 pole, 2 poles, 3 poles, however many they can get. They discover that for 4-particle scattering, we can have poles on the S channel or the T channel, but not both of them. For 5-particle scattering, you can have poles when S12 goes to 0 or S123 goes to 0. These are the sum of the momentum P1 plus P2 squared or P1 plus P2 plus P3 squared. And the cyclic rotations of this, but not any other combinations. So there's an interesting pattern to which poles are allowed to come together. And they would notice that this pattern can actually be represented graphically. For example, in the case of 5-particle scattering, the first poles that would involve sort of 1 particle, a 1-particle factorization channel, can be thought of as the edges of a pentagon. And the sequence of 2 poles that come together correspond to ways of taking this 4-particle amplitude on one side and factorizing it into the product of 2 3-particle amplitudes in 2 different ways. So you see, it's slightly non-trivial, that quite non-trivial. These examples are a little small, but that the pole structure that are associated with these amplitudes are polytopal, that you can associate them with a picture in this way. The case of four particle scattering is particularly simple. It's just an interval where we get the two factorizations on the boundary. Now, when we go to, and if I represent the same picture in terms of triangulations, it's just saying that in these examples, there's a geometric space, either an interval or a pentagon, where I can think about the vertices as complete triangulations of the polygon and the edges as partial triangulations. Now, this is more interesting when we go up to 6 points, where it takes a lot more imagination to see that you can do it, but in fact, you can do it. And this was famously discovered by Jim Spacetime in the 1960s. There is a polytope. In fact, it wasn't until the 1980s till people realized that it was actually realizable as a real polytope with flat faces like this. Anyway, it's possible to represent this combinatorics, all the diagrams, all the triangulations of the polygon or all the cubic graphs dually can be thought of as vertices of a shape that lives in n-3 dimensions, with all of the facets corresponding to partial factorizations or partial triangulations of the polygon. Okay, so that's the associahedron. And I want to emphasize that the particle in the string picture don't make this fact obvious. This is some sort of simple, interesting, qualitative fact about the pattern with which the poles come together, which is not obvious from the particle picture, not obvious from the string picture, but is true. It's interesting that this fact actually implies everything that's known about the particle in the string picture, however. For example, factorization is seen nicely in the associahedron and is reflected in the fact that the boundaries of the associahedron, the facets that are the boundaries of the associahedron, are actually products of lower associahedra. We see that in this, we see that in this example. I'm just drawing it again in terms of triangulations. You'll notice that this lovely object has 6 faces that look like pentagons. The 6 faces that look like pentagons, if you remember, the 5 particle scattering was a pentagon. So that's nothing other than the factorization with 5 particles on one side and 3 on the other. And there are 6 of those, and those are the 6 pentagonal faces. We also have 3 square faces, and remember that the 4 particle scattering was an interval, and the square is just the direct product of 2 intervals. Okay, so from this picture, we see both that the combinatorics is polytopal, which is non-trivial, and we learn about factorization. Okay, so our goal now is to try to make this obvious, and making this obvious is going to be a qualitative clue for the sort of theory that we're looking for in kinematic space. I want to make one more quick comment on the fact that it's not just a sort of seemingly qualitative fact that the combinatorics of poles is polytopal, but there's actually a sharper fact. There's a certain hidden symmetry that these amplitudes have, which we don't see when we talk in terms of Feynman diagrams. Even these stupid phi cube theory amplitudes have a hidden symmetry. And in order to see the hidden symmetry clearly, we actually have to upgrade from the amplitudes, which are functions, to certain differential forms. So instead of writing down, for example, at 4 points, 1 over s plus 1 over t, we'll write down ds over s and dt over t instead, or in the language of these x variables, dx13 over x13 and dx24 over x24. And the interesting point here is that, in fact, we shouldn't put a plus sign, but we should put a minus sign. Now, what is that minus sign accomplishing? There is a very natural thing that one would want to have. One would like to think that these objects don't depend on the overall scale of the x's, that after all have units, but only depend on the ratios. In other words, we would like the forms to be well-defined on the projectivized version of the space of all the x variables. And asking that to be the case forces this sign here in the case of 4 points. At higher points, it's actually much more non-trivial. We have to demand the invariance of this n-3 form under this projective rescaling. And that means that, that under this rescaling, the coefficient of this rescaling parameter, d log alpha, multiplies all diagrams which have just shrunk one of the propagators. So demanding that the form is projectively invariant ends up imposing many, many more equations than unknowns. So it's not at all obvious that it's possible, just by equating an unknown, to choose the signs to make the form projectively invariant. but it can be done. Remarkably, that's a hidden symmetry. It's possible to choose the sign so that this form is projectively invariant. This is an interesting symmetry, even of this dumb phi cube theory, but is the analog of the dual conformal invariance of n equals 4 super Yang nulls in a quite precise sense. It's an analog of that famous hidden symmetry of n equals 4 super Yang nulls. And the existence of this polytope makes the symmetry obvious in a way that I will try to, well, in a way that we'll see in more detail as we proceed. Finally, so here we see that we're not looking for a function on kinematic space. We're looking for a differential form on kinematic space. It's this n-3 form on kinematic space. How do we go from this form to the function? And the answer is very simple. For example, in the case of 4-particle scattering, we have a 1 form on this 2-dimensional space of x13 and x24. So we have to find certain natural families of subspaces. So here is one, just where x13 plus x24 is a constant. And if I pull back the 1 form to this 1-dimensional space, the minus sign goes away, and what multiplies the overall trivial volume factor on this subspace is the actual amplitude. Okay, so and this ends up working in general. I'll describe what these letters mean a little more later, but there's a natural subspace that one can pull back this projective form onto, so all the minus signs go away, and what you get is literally just the amplitude. So I've given you a few sort of hidden facts about the amplitude. The pole structure is polytopal. Thought of as a differential form on kinematic space, it's possible to magically choose these signs so that the whole form is projectively invariant. And it's possible to find some subspace to pull back the form to where all the minus signs go away and you literally just get the sum over all the amplitudes. So all 3 of these are sort of interesting facts about this form. All 3 of these are facts that are made obvious by the existence of the associahedron polytope in a way that I hope will become clearer as we go on. So in fact, about 2.5 years ago, some friends and I ran into a particular realization of the associahedron, not just this sort of combinatorial picture, but a very specific realization of the associahedron that I'll talk about a little bit more. So you'll see that in this picture, the combinatorics is exactly the same. There's still 6 pentagonal faces and 3 square faces and so on, but it has a very specific shape. There's lots of faces are parallel to each other and so on. And it was quickly realized that this way of realizing the associahedron was intimately connected to cluster algebras, and in fact the set of polytopes is associated with all cluster algebras. So again, continuing with our with sharpening our general question, we came up with this realization of the associahedron sort of by guesswork and by various physics motivations. But we'd like to understand more deeply, where does this object come from? What question would we ask in kinematic space that would directly land us on this? Okay, so now I'm going to proceed for the next 10 or 15 minutes, assuming that you don't know anything about cluster algebras and just asking simple questions in kinematic space. Ultimately, we'll get somewhere where it will really pay to think about the cluster algebras, and at that point, I will transition. But we can go quite a distance without explicitly talking about them. So that's how I will begin. Okay. Maybe we can stop right now because we're now going to transition to the sort of second part of the talk. Are there any questions so far?
I don't believe there have been any. In
great, very good. Okay, so let me continue. All right. So now forget everything. Let's start over. Remember, our goal is to find some question to ask in kinematic space whose answer will end up exposing this associahedron and the scattering form and all the rest of the things that we're talking about, okay? So what is our kinematic space? It's just a space of these dumb variables xij. So that's a special case of the general challenge that I keep alluding to. We don't have any kind of metric, locality, time. We just have the space of xij's. In this space, we have to ask some question that's going to bring all bring all these structures to life. So how's that going to happen? Well, we're going to begin just by graphically denoting our variables. So, and it's sort of obvious what to do because we have a cyclic structure. So I'm just going to plonk them down on a sheet of paper. Okay, so here I'm going to write the variable x13, x14, x15, x16. This is for the case of 7-particle scattering. Okay, and x12, remember, was one of the edges of the polygon, so it's 0, and x17 is also 0. Okay, so if I just do this, I fill out this grid, and I've drawn it vertically just because it's natural. Because we have boundaries where things vanish. So 1, 2, 2, 3, 3, 4, etc. vanish. Okay, so I've just drawn all the variables on this grid. And now we have the first little bit of magic which happens, which is that there's actually a natural causal structure on this kinematic space. We should really think of it as a kinematic space-time. So just to emphasize, this time and space has absolutely nothing to do with the time and space in space-time, in ordinary space-time, but there's a kind of a causal structure in this kinematic space. Why is that? Well, what is this causal structure reflecting? Well, to begin with, if I label a variable here, ij by xt, then I have ij and ji are the same. So there's an interesting Mobius identification on this guy, where x and t is identified with 1 minus x and 1 plus t. Okay, but the more interesting thing is we've seen already that that it should matter whether chords cross or not. The crossing or not of chords is an important feature of this story, and whether chords in the polygon cross or not. In fact, when chords in the polygon cross, that means something that has a very interesting causal interpretation in this picture. Two chords that cross means that the two chords, in this case ij and kl, can be thought of as the past and future corners of a causal diamond that fits in this kinematic space-time. Okay, so if the chords don't cross, they're either space-like separated or they're so far separated in time that the light cones don't intersect each other. But if the chords do cross each other, that means that they fit as past and future corners on a causal diamond that fits in the space-time. So that's the most primitive sort of combinatorial reason why there's a natural causal structure on kinematical space. And so another comment is that given this band, we actually have to make a choice to take a chunk out of the band if we want to cover each one of the xij variables once and only once. So I'll draw this picture a lot of the right triangle here, but there are lots of ways of doing it. And you'll see what's important here is that I've chosen, for example, 1, 3 is inside the region I'm talking about, but 3, 1 out there is not. Okay, so any way of covering, any way of taking a chunk out of the space that covers all the variables once and only once is legal. And I'll be drawing this one with that chunk of the right triangle. Okay, so those are our variables. And now we have to ask a question. We have to ask a question in this kinematic space. And what is the question going to be? Well, we're just going to solve the wave equation. That's all. We're going to solve the wave equation in kinematic space. So if I switch to the usual light cone variables u and v that go off on 45-degree lines, in the continuum, the wave equation is just du dvx equals, I'm going to have a source, little c. And there's only two facts you need to know about the wave equation for what's coming next. One of them is that you can think of the sort of global, the integral version of the wave equation, the Gauss law in 1 + 1 dimensions, just says the following. For any causal diamond in the 1 + 1 dimensional space, the value of past plus future minus left minus right is the total charge inside that diamond. Okay, so that's Gauss's law. And there's another simple fact, which is that if you're given, well, I'll call the scrunch rule, if you're given a solution of the wave equation outside some 45-degree region here, x right and x left, then you can make another solution of the wave equation simply scrunching that region away and replacing the charge that was in there by some delta function source at the adjuncture. And that's obvious from the Gauss's law, because if you only care about the values of x on the right and the left, then everything that you get from the Gauss's law in this picture is the same as what you get from this, from the picture on the left, the same as what we get from the picture on the right. Okay, so that's we're asking this dynamical question in kinematical space-time, just solving the wave equation. But we're going one more ingredient that we've seen many times in this story, but now we're going to in this more general story of amplituhedra and scattering amplitudes, is that the word positivity has to make an appearance. And so we're going to do that by asking for positive solutions to the wave equation. What that means is that we're solving du dvx equals c, but we want x to be positive, also the sources to be positive. So remember, x is 0 on these two boundaries of my chunk of space-time here. And so what I'm asking is to put some restrictions on the initial data here on the past so that x stays positive everywhere inside, so long as the source is positive. So we're looking for positive solutions of the wave equation. And remarkably, positive solutions of the wave equation put restrictions on the past data that forces that past data to lie inside the associahedra. Okay, so that's how the associahedron makes an appearance in this story. So for instance, if instead of asking for x to be positive everywhere, I only keep track of its values at a finite number of points to begin with. So let's say I only care about the values of x on this past boundary at 1, 3, 1, 4, and 1, 5. Then I just shoot out the light rays into the interior of the space-time, and I bring to life all these intermediate points. And I can solve for all these intermediate points using Gauss's law, and I just demand that they're all positive. And that puts a bunch of positivity restrictions in the space of x13, x14, and x15. So it forces the values of x at 1, 3, 1, 4, and 1, 5 manifestly to live inside a particular polytope. Remarkably, that polytope ends up being exactly the ADHY associahedron that we sort of randomly guessed from physics points of view long ago. And exactly this picture, in fact, generalizes and describes all cluster algebra polytopes in a way that I'll try to describe quickly. But let me try to explain conceptually why this has to be the case. This has to be the case because this picture of the positive wave equation actually explains factorization as well. So that's really what we wanted. We want a picture which is manifestly polytopal and which on the boundaries, but where it's also obvious that we go to a boundary of this polytope, what we get is the product of two lower polytopes of exactly the same type. And that has a beautiful one-line explanation here. So let's say I have a positive solution of the wave equation, and I want to go to a boundary, which means I put x to 0 here at this special point x star. Then it's natural to ask, where else can I put x to 0? And the answer is very simple. If I shoot the light cones, the light rays out of this point, all the points here in red, which would give me other points, which would be either past or future corners of a causal diamond involving x star, I can't put them to 0 anywhere. The reason is that if I could, I would violate the positivity in this Gauss's law. Remember, Gauss's law tells me past plus future minus left minus right is a constant. So if past and future go to 0 and everything is positive, I would have the sum of two negative numbers equals a positive number, which is impossible. So I can't put x to 0 anywhere inside this red region. And furthermore, I can reconstruct everything in the red region simply from the knowledge of what's going on the boundaries, again, trivially using Gauss's law. So I can scrunch away those two regions if I want to describe all the solutions of the wave equation, having put x star to 0 here. I can scrunch everything away and I get exactly the direct product of two smaller questions of exactly the same type. So what this picture of the positive wave equation in kinematic space is made manifest is that we have something polytopal, which has the property that on the boundaries it factorizes into exactly objects of exactly the same type, but smaller objects of exactly the same type. Okay. Finally, what determines the scattering amplitude? Well, as I mentioned, the scattering amplitude is actually a differential form, and the scattering form is the unique form that's defined on the spaces of all these xij's with the property that when you pull it back to a solution of the wave equation, you get the canonical form for the associahedra. This fact that it's associated with this polytope makes the projective invariance completely manifest. In slightly more detailed facts, which I don't have time to explain, also tell us that when we pull back to this subspace, it's guaranteed that all the signs go away and we just get +1s. And so the canonical form pulled back to the solution of the wave equation exactly gives me the volume form on the subspace multiplied by the amplitude. And finally, Feynman diagrams are just one particular triangulation of the associahedra. So if you want to get the actual canonical form, you can triangulate the associahedra any way you like. If you apply this universal way of triangulating simple polytopes that I mentioned before, that form is known as Feynman diagrams, because it goes to every vertex of the associahedron, and you multiply the d log of all the variables, all the face variables that meet that vertex. Remember, every vertex is associated with a triangulation of the polygon, dually the cubic graphs of the cubic Feynman diagrams. So this triangulation of the associahedron returns what we normally call Feynman diagrams. But there are many other triangulations that are possible. And in fact, the Feynman diagrams have a defect that term by term, they make it appear that there's a pole at infinity that only cancels in the full sum of everything. So the Feynman diagrams obscure the projective invariance of the answer. It's possible to give many other triangulations that manifest a projective invariance, and I'm not going to talk about any explicit formulas here, but suffice to say that this picture is sort of vastly more efficient than ordinary Feynman diagrams are, even for this simple cubic scalar theory. And I'll just mention here in passing that there's a number of general methods for computing the canonical forms of polytopes that have been developed over the past couple of years, and one of those methods actually has a parameter alpha prime associated with it, and if you apply that general method to this particular polytope, you get string amplitudes, not just a field theory amplitudes, but an alpha prime deformation of these amplitudes that are directly what you get from the Cope-Nielsen formula. All right, so maybe I'll stop here and ask if there are any questions. I saw a number of things went up in chat, so maybe we can take a quick look here.
There are a few. Just to go through some of the leftover ones. There was one about algebraic relations among the Xij.
Yes, there are none.
Are there any?
Sorry. I should make that this is an important point. The Xij's are just quadratic in the momenta, if you live in a fixed number of dimensions, like 4 dimensions or 8 dimensions, then eventually there are these so-called gram determinant relations, simply because of the fact that I can't have d plus 1 independent vectors in d dimensions. So there are relations involving determinants of these invariants. But those relations are irrelevant to the calculation of the Feynman diagrams. So in a sense, what we're talking about is valid in the limit of any number of dimensions, or if you like, the number of dimensions going to infinity, where there are no relations between these x's. If we live in a fixed number of dimensions, then we'd have relations between the x's.
And the other one is whether it's obvious that unitarity arising from the factorization of the geometry explains Kutkowski's rules.
Yes, I mean, this is just a simple example of Kutkowski rules at tree level. We'll be seeing sort of loop examples, well, depending, I have 10 minutes left, so we'll see how much we'll actually see. But yes, but maybe I can answer this question more invariantly. At the level of the sort of final amplitude, where we integrate over all the loop momentum, we get these complicated transcendental functions of the external variables. To this day, in the year 2020, we don't know what the rules are that lets us read off whether the result is compatible with causality and unitarity in space-time. Okay? However, we can do a lot better by looking at what you can call the integrand of the amplitude. Before you do all the integrals over the loop variables, and at the level of the integrand, which is what Kutkowski tells us to think about, then indeed, unitarity, locality and unitarity are, as we've seen at tree level, where the poles are and a certain factorization on those poles. But it's a different kind of factorization when we go beyond tree level, because we have to cut the internal loop variables as well. And we'll see perhaps at least quickly an example of that as we go on. Were there any other questions? Yeah, somehow, I'm sorry, I don't see what all the chats are here. Ah, okay, here. Okay.
There is one that just briefly appeared, but you can take it at the end.
So let's. Okay, great. Yeah. All right, so let me proceed. Okay. So let me keep going here. A little bit, starting to head towards clustery thoughts, but again, still asking sort of natural questions in this kinematic space. The way I describe thinking about the solution of the wave equation is sort of globally by imposing Gauss's law. But we can also obviously think about it locally through sort of time evolution like we normally do. So here's a picture. I can start with this initial surface in the past, and what time evolution is just using the smallest meshes in this picture, which are the tiniest Gauss's laws. So those are the discrete analog of the wave equation to predict the next point. So I start from 1, 2, 3. I can use this little mesh here to predict 4, the next little mesh to predict 5, and so on. And in this way, I can go through the entire space-time. Now, we can actually abstract away what we're doing here by drawing an associated quiver. There's a very simple associated quiver here, where given this 1, 2, 3, I draw this quiver x1 arrow to x2 arrow to x3. And the arrows are such that there's an arrow from A to B simply if A is on the path of B. That's it. Now, this picture of time evolution in the kinematic space-time is actually represented by a very simple move on the quiver, where I just take every source and I quote unquote mutate on it, where here it just means I introduce a new variable and I reverse all the arrows going into the source. Okay, so if I do that, and then I write down this equation, xv plus xv prime minus the sum of all the w's with v goes to w of xw equals a constant associated with that vertex. Okay, so this is a way of abstracting away the picture of time evolution to a simple set of moves on this quiver. I don't have time to describe it, but in this picture, you know when you stop. At the level of the quiver, it's maybe not so obvious where to stop, but there's a very natural place of stopping, because in fact, as you go, you can think of this as carving out the polytope we were talking about one face at a time. And so you just keep adding a face and a face and a face until you're done carving the whole thing out, and then you stop at that point. So it's possible to specify the rules for how you mutate and when you stop in a completely intrinsic way without making reference even to the underlying kinematic space-time picture. And you can actually abstract that whole idea away, once we've described it in that way, to any old quiver. So we're going to abstract away the notion of time evolution in a way that can be associated with any acyclic quiver. Okay, so I start with any quiver that doesn't have any cycles, and I just decide to mutate on all the sources, and I write this equation down as I go along. So the people who know about cluster algebras, this is just the Auslander write and walk. Okay. Now, interestingly, this is now a rule that you can define on any acyclic quiver, and you can just ask, when does this rule actually give you a polytope that eventually ends up closing? And the answer is only when the quiver is an orientation of a Dinkin diagram. This is a very interesting fact, but only when the quiver is an orientation of a Dinkin diagram is this true. And what you get from it is in fact, the sort of generalization of this ABHY realization of the associahedron now associated with every Dinkin diagram. And these are the polytopes associated with cluster algebras, finite-type cluster algebras that are also in bijection with Dinkin diagrams. Okay, and so now we're starting to talk more about cluster algebras. So just to say what the general story ends up being, cluster algebras that are finite are associated with Dinkin diagrams, and all the classical ones actually have an interpretation in terms of physics. The corresponding polytopes have an interpretation in terms of physics. For type A is just what we talked about. These are tree amplitudes. Type B and C, the polytopes end up being the same, and you can actually interpret them as one loop amplitudes with the emission of tadpoles. Type D is general one loop diagrams. We don't have yet a physics interpretation for what the exceptional finite what the polytopes corresponding to exceptional finite Dinkin diagrams are. So it'd be interesting to find a physics interpretation for them. But beyond that, we have to talk about when we go to higher loops, we're actually dealing with infinite type cluster algebras. And as we'll see, the cluster algebras of punctured surfaces. Okay, but just to give an example of what things look like at one loop, what is it that you would do at one loop? Well, we would draw, let's say, Feynman diagram. We draw Feynman diagrams that look like a box like this for 4 external particles. When we look at the dual of this diagram, we get the triangulation of a square, but where we have a puncture in the middle. Okay, so now we're talking about triangulations of a polygon with a puncture in the middle. But once again, if we just think about what these sort of kinematic space-time variables look like, for example, there's a little difference already that we can have xij is not necessarily the same as xji, because they can wind around this puncture in different ways. And we have this new kind of variable that goes from the outside to the that goes from the external points to the puncture that we can think of as the loop variables. And there are some interesting technical points about how to deal with these self loops that cluster algebraists know all about. We're not allowed to draw these self loops. Instead, we have to draw what are the so-called tagged arcs so we have to have two kinds of arcs that go from the outside to the inside. But anyway, there is a simple kinematic space-time picture at one loop. And this is exactly the same as what we did before. We take all the kinematic variables, we draw them, and we draw them by starting from one of the variables and applying the cyclic action on it, exactly the same way we did before. You can see here that we have a little Dinkin diagram there, like for D4, 1, 1 tilde, 1, 2, 1, 3, there's a little Dinkin diagram there, and it's filled out into this mesh. And once again, the solution of the wave equation in this kinematic space-time, exactly the same things happen. We get a polytope. The corresponding polytope is the cluster polytope for Dn, and physically it calculates one loop, the integrand for one loop scattering amplitude. So there's a picture for what the D3 polytope looks like. Okay, so I have 5 minutes, right, Tudor? Is that right? Tudor?
Yes.
Okay, great. Okay, so in my remaining 5 minutes, let me just give you let me give you a flavor for what these these finite-type cluster polytopes for associated with the classical Dinkin diagrams. These are the clusterhedra for tree and one loop amplitudes. But now I want to give you a flavor of what the challenge is in general. So to do that, let me just first tell you something extremely simple, that on what the general correspondence is. We want to look at Feynman diagrams for not just single trace, but single, double trace, maybe even zero trace for vacuum diagrams, but H trace Feynman diagrams drawn on genus G surfaces with L loops. So that's what we have on the Feynman diagram side. But remember, this entire story, we've been looking at the duals of those diagrams. So the duals of those diagrams are the triangulation of a closely related surface with H boundaries of genus G and this number of punctures, L plus 1 minus 2G minus H punctures. So for example, if we talk about the two-loop genus 1 vacuum diagram like this, we would draw it on a torus. But then when I draw the dual of this picture, I get this one. And the dual is a triangulation of a once punctured torus. Okay, so in general, we're talking about triangulations of surfaces with some number of punctures that are determined by the underlying loop and genus order of the diagrams that they came from. And we've seen that the diagrams themselves can be thought of as vertices of these interesting polytopes that are associated with cluster algebras. So let me just very quickly mention some basics about the cluster algebras. It's an extremely simple object to define. We start with any old quiver that we like, and we can think of this as some initial cluster. And then there are some simple rules for how to make a new quiver. There's a notion of a mutation at a vertex V. I'll just write them down here. I don't have time to explain it in detail. But also associated with that mutation is we can also associate the variables with all these vertices. And there's also an expression for what the new variable is after you do the mutation, given by this interesting formula. The product of the old and new variables is the sum of the product of everything coming in to V plus the product of everything going out of V. It's interesting that that there's also a kind of a linear version of these formulas that we can get by tropicalizing this expression. And when you tropicalize, there's sort of two linear expressions that we could get. In the tropicalization, there's normally a notion of a max here, but for my purposes, I just want to record the two linear versions of this relation, where I get xv, the capital XV plus xv prime, either minus the sum of all the vertices going in, or all the w's that are connected to V out, or all the w's that are connected to V in. Okay, so there's a cluster algebra associated with surfaces. Clearly, we're interested in triangulations of surfaces with the punctures, and the quivers arise from triangulations of the surface. So here's a very simple example. If we take this hexagon, then in order to get a quiver, you triangulate it. You put a dot in the middle of all of the internal. You put a dot in the middle of all the edges of the triangulation, and then you draw these oriented triangles inside each one of the triangulation and read off the corresponding quiver associated with them. The beautiful thing is that the obvious move at the level of the triangulation of the quadrilateral flip, where I take this edge and I replace it with that one, and going from one triangulation to another, is exactly the quiver level of mutation relation. And also, very beautifully for the surfaces, the mutation rule, also the algebraic mutation rule, are nothing other than the ski relations that you would draw on the surface. It was a little bit of extra thought about what happens when you deal with these tagged variables, but I won't say any more about that. Okay, so if we're interested in thinking about the all loop, all orders in 1/n bi-adjoint theory, and we've already seen the 3-to-1 loop, they're captured by these interesting cluster polytopes. Well, in general, when we go to two loops, for example, I have to have a triangulation. Let's say two loops in the leading planar limit. I'd have two loops, so just two punctures. So I have a surface with two punctures and some number of boundary points. Okay, so the corresponding quiver for this guy is not dn, but dn plus 2 tilde. Similarly, I can keep going. If I have two loops, the leading 1/n correction, so I draw it on a torus. Okay, so I draw any picture that I want. I draw the corresponding dual. It goes along with this quiver. In all of these cases, beyond one loop, the corresponding cluster algebras have this interesting property of being infinite. So we have to deal with the infinity of these cluster algebras. That means that everything about them is a little bit more confusing. If we want to think that there's some kind of polytope that captures all of the diagrams, well, naively it would have to be infinite. And then it's not so obvious how to think about it. There isn't some existing literature of how to think about these infinite polytopes and so on. So let me just, so there's a whole story here about, which I don't have time to talk about. If people are interested, I'll be happy to explain more later. Before getting into these novelties of Clusterhedra, why there's I think a deep connection between some simple and deep facts about the so-called G-vector fans of cluster algebras and space-time locality and unitarity. But let me skip over that and just give a flavor for what the challenge is. The challenge, where this infinity comes from, and what the flavor with the challenge, what the flavor of the challenge is to dealing with it. So here's the problem. So let's say we talk about a triangulation of a surface with two punctures here. The difficulty where we have these infinitely many variables is simply there's an infinite action of the mapping class group on the surface. In other words, I might like to think that this variable, there's just one variable of this type, and if I'm drawing a dual Feynman diagram, there would just be one variable that's dual to this. But from the perspective of the triangulation of the surface, I have this variable as well as all the other ones that wind around the other punctures some number of times. And I can think of getting all these variables by just taking these two punctures, taking them out, rotating them some number of times, that's the actual mapping class group, and shoving them back in. At L loops, the mapping class group is in fact the braid group on the L punctures. And so that's where the infinity comes from. So somehow there's this infinite action of the mapping class group, and we like to mod out by it somehow, but there's no obvious way of, there's no totally obvious way of modding out by it. And perhaps but what we're looking for is some way to make this infinite thing finite, some way to naturally compactify it. And that's what these clusterhedra are meant to be. These are supposed to be polytopes where the vertices are unambiguously associated with diagrams or clusters. These so-called G vectors that I haven't had time to define, but the G vectors associated with the cluster variables are among the facet normals of this polytope. Its projective invariance will be trivial, but it should have the property that when you pull back the differential form on the subspace defined by the clusterhedron, we get this remarkable property that we get all plus ones. Another way of saying this is all the normal vectors of the facets of this object should have determinants plus or minus one to the facets that meet at a vertex. So that's what we're looking for. But it turns out that it's actually sitting there all along, that we don't have to invent it, that this kinematical space-time has a richer structure at multi-loop level, and we'll actually see these clusterhedra naturally living there. And the essential idea we can illustrate in this very simple example. Here is what we would get, for example, beyond the planar limit. If we want the double trace at one loop, we would draw a picture that looks like this. This surface is also associated with a certain class of so-called cuts of the loop amplitude to all loop order. So exactly this AN1, N2, or ANL is the sort of first new example beyond the finite ones that we've been talking about that's relevant at one loop to double trace terms, and also a certain class of infinite loop order cut of the amplitude. And if we just look at the kinematic space-time, we have various kinds of curves that we can draw. We can have sort of out curves that connect the boundary on the outside. We can, and similarly in curves, we can have these interesting in-out curves, which are the ones which have this infinite winding that goes along with them. But the crucial point is that there's another kind of curve, obvious in the surface, which is just the guy that goes around. Okay, so now this guy is not a cluster variable. Obviously, this does not show up in any triangulations of this surface, but it ends up playing a crucial part in the story. And if you just sort of follow your nose, I'm not going to go through this in any detail, but just the high level statement is you just follow your nose and just look at what the kinematical spacetimes look like. You look at this in the kinematical spacetime involving the in-out variables, and it's much the same story as we saw before. You still get a strip, but you get an infinite cylinder, and it's infinite because you can keep winding forever. So that's the sort of infinite winding, is that you can, in principle, have this cylinder that goes off to infinity. You can have the variables involving just the out-out and the in-in ones, and those are finite, but they also have a nice mesh natural kinematic spacetime associated with them. The key point is that there is a natural way of stopping this winding and compactifying using delta. In the end, there's a picture for the full kinematical spacetime where there's a part that involves just the in-out variables. There's a part that just involves the out-out and the in-in variables. All of these are naturally have relations which talk to each other, but there's no way canonically, naively, only using cluster variables to glue everything together, to glue the sectors where the variables wind a lot in one direction and wind a lot in the other direction together. But delta does it for you. Delta is kind of like gravity and couples all sectors to each other. And in order for this to work, there are certain relations that have to be satisfied between the G vectors of the cluster variables as well as delta that are non-trivial. It's not obvious ahead of time they have to be satisfied, but they are, and that's the sense in which the structure of this the structure of the G vector fan of the cluster variables together with the delta is actually begging you to make them into a clusterhedra. So I think I'll just end with that, just to say that what we understand completely are clusterhedra for the case of affine type cluster algebras. Exactly the same ideas that I just described work for the affine type D case, which is two loop. So we have concrete clusterhedra through two loops and all loop order, and certain cuts of any loop order in this ANL example. In these examples, delta, once we stop, once we cut off this infinity, there are naively missing cluster variables. And the remarkable thing is that delta is the stand-in for every missing variable in every direction. And that allows us to unambiguously associate all the vertices of this clusterhedron with diagrams. All the vertices that don't have to do with delta are counted the same number of times. And all the normal facets also involving delta give us plus minus 1. So again, we get these for the determinant. So we get all plus 1s for the amplitudes when we pull back. Here is a concrete picture for what the three-dimensional, it's one of the few examples that's low-dimensional, of course, to draw, but this is what the A21 clusterhedron looks like, where I've highlighted here what the delta facet, what the facet involving this new delta variable looks like. So we're done through 2 loops, some all loop cuts. We're on our way to all loops and all orders in 1 over n. The basic strategies to understand these decoupled sort of topological sectors involving the action of the mapping class group, and add these deltas that correspond to closed loops on the surfaces that should sort of gravitationally couple all the sectors and allow us to compactify. And I'll just flash this fascinating thing that we're in the middle of exploring. The real novelty, it appears, beyond the affine type, is that the kinematic space is no longer just sort of flat, like we've seen so far, but is in fact cosmological. The variables grow in a cosmological way. The simplest example is already seen in the case of the once punctured torus. So this is the first thing that we can talk about beyond the interesting beyond the planar limit. The corresponding quiver is extremely simple and famous. It's known as the Markov quiver. The cluster variables are just associated with. So here's a triangulation of the once punctured torus where I've opened up, unwrapped the torus. The triangulation, the cluster variables are associated. The variables that you see in the triangulation are associated with lines of slope p over q in lowest terms, connecting the punctures. The deltas, that are the closed loops on the surface, are just lines of slope p over q that miss the punctures. So we have the same number of them. But if you just look at what the cluster structure looks like, it grows. It grows like a Markovian process, or you can associate it with a Fairy diagram in a natural way. And it looks like de Sitter space in kinematic space. So the variables grow, but it still is true that if I just look at the variables that I see in the triangulation, so this is a picture of what the normal facets of the clusterhedron look like. If I just look at the ordinary cluster variables without delta, I would get this jagged thing here drawn in green, and it doesn't close up naturally. That's why you naively have to keep on going to get this infinite fractal picture, but it's always missing something. However, you can stop at any finite point and add in the corresponding deltas that you've seen up to that point, and that beautifully fills out the whole space. So again, the deltas is now more than one of them, but they allow us to compactify the space and give us a corresponding clusterhedron. So that's the first example where we see something cosmological. And we see something even more interestingly cosmological when we go to the case of even genus 0 surfaces, but with more punctures. Starting at 3 punctures, we have the non-abelian action of the mapping class group on the 3 punctures. In fact, if you just want to label the arcs that you could draw in this picture, even in the simplest case with 1 point on the outside and 3 punctures in the middle, then that's already just labeling the arcs is an interesting exercise. They're labeled by cosets of the braid group on 3 strands mod the braid group on 2 strands, which turns out to be the same as the free group on just 2 variables that you can think of as the rotation of the interchange of the first 2 of 1, 2 and of 1, 3. And so all the variables are it's not even like we saw in the Markov example where it's like one space-time. Instead, we get this sort of Cayley tree picture that looks a little bit more like things that we've seen in physics in the context of eternal inflation. So, there's this exponential growth of the variables, which is the hallmark of what happens beyond the affine type case. And that's just something I think we understood a lot of how it works in the Markov example and the associated clusterhedron, but that's what we're in the middle of trying to understand now. All right, so let me end. I'm sorry I went over time. Just the general outlook, over the past few years, we've been seeing quite concrete examples where the rules of space-time and quantum mechanics, locality and unitarity, as concretely showing up in locality and unitarity of scattering amplitudes, are seen to emerge from some simple new structures and questions that you can ask directly in kinematical space at infinity. This was, as I said, was first seen in the case of all loop planar n equals 4 super Yang mills and the story of the amplituhedron. There you could say maybe that's something to do with supersymmetry or integrability or some very special things about this theory, although to those of us working on it, it was totally clear it had nothing to do with integrability, at least. But anyway, you could think that as somebody with very special properties of that very special theory. Now we're seeing very similar things in a completely non-supersymmetric context, this bi-adjoint phi cube theory, which really is the singularity structure of any color theory to any order in 1 over n. And we're heading towards understanding it at all loop order and all orders in 1 over n. As I said early on, what's important about these ideas to me, certainly what drives me to study them, is that they're directly related to real world physics in a reasonable approximation. Again, the world we see in the window outside, when we look in the window outside, they expose hidden symmetries even in places we didn't expect to see them, like the simple scalar field theory. And they describe certain universal features of the singularities of a wide class of theories. And there are many open questions. We don't know, for example, even though there are lots of intriguing hints of connections between them, we don't know how the amplituhedra and clusterhedra are related to each other. Especially the story of clusterhedra is clearly related, should be related to string theory in an interesting way. We're talking about Riemann surfaces. Anyway, there should obviously have some interesting relations to string theory, and we've already seen some interesting relations to string theory just in the story of the ordinary associahedron. So we'd like to see how that carries over to the rest of the even finite-type cluster polytopes as well as clusterhedra. There's a sort of fascinating fact that this object delta has lots of qualitative similarities to what we think of as qualitatively gravitational features about it. It sort of universally couples different sectors together, and in some somewhat precise senses, the singularities that are associated with delta, sitting on those facets of clusterhedra, we see factorizations which are reminiscent of the factorization that you'd expect on graviton poles in string theory. When we understand how gravity emerges from one loop open strings, closed strings emerge from one loop open strings in string theory. So we'd like to understand if that's more than an analogy, and of course we'd like to understand how these things could extend to more general theories. All right, thank you very much, and sorry again for going over time. Thanks.
Thanks so much, Nima. There was one question left over from the chat, and otherwise I will wait for folks in the audience to raise hands. So from the chat, there's a question about Weyl groups acting on Dinkin diagrams and whether they play any role in your picture.
Yeah, I mean that's you know, when you go from one, if I understand the question correctly, when I didn't have time to talk about these G vectors and clusters, but essentially cluster algebras are very nonlinear things. But there's a sort of way of talking about them as linearly as you can that associates, given some initial cluster, it associates a vector with every cluster variable, and with every cluster, so every collection that occurs in a quiver, you get a certain cone. Now, the remarkable thing is that those cones are non-overlapping, and in the finite-type cases, they're non-overlapping and they cover all of space. And you can go from one cone to another by doing a mutation. So when you do a mutation, one variable changes, and roughly the one variable changes in a way that it reflects through the other. So that's how you go from one cone, and you see that it doesn't overlap with the other one because it reflects across the sort of plane made by the other ones. So yes, so that's so those are the that's some of the action of the reflections. And the thing that I didn't get to talk about is, but I want to, maybe I'll just say it now, it really is remarkable that these cones are non-overlapping and that they cover the space together. It's remarkable because you start off not knowing anything about, you don't care about triangulations of the surface, you don't care about adding a bunch of things together. But the cluster algebra structure tells you that these G vectors want to come together in combinations. These cones, first of all, the ones that come together in the cones are exactly the ones that we can ascribe to local spacetime processes. And secondly, that the cones want to tile all of space together. So that's the reason for adding them all together. In the ordinary way of thinking about things, locality is put in by hand, and then you add everything together because quantum mechanics tells you, the path integral tells you. This is an alternate picture for why you take the objects together that we normally associate to local spacetime processes, and why they should be added up together. And again, as we've seen over and over in this general story, both those things, the sort of spacetime locality and the unitarity that tells you to add all these guys up together, is a fact about this one deep fact about the G vector fan. That's precisely true for finite type, and in infinite type, one of the novelties is that this fan doesn't cover all of space. So all these cones don't cover all of G vector space, and it turns out for the case of surfaces, it almost covers it in the sense that it misses lower codimension regions. And somehow the story of these deltas is about allowing you to fill out the space in a more, to go for a while, stop, and naturally fill and compactify, fill out the whole space in a different way.
Thanks, Nima. So I think Jacques Dissler had his hand up first. Jacques, would you like to unmute yourself?
Yeah, so in this bi-adjoint phi cube theory, there are, unlike in n equals 4 super-Yang mills, there are ultraviolet divergences. So for instance, in 4 dimensions, I'd expect there to be an elementary quartic interaction, which would be required in order to renormalize the theory. Where does that enter into this story? I mean,
No. So Jacques, first of all, there is no such thing in 4 dimensions because there's no such, well, I mean, this is besides, you'll see in the second one, this is besides the point. But in 4 dimensions, the phi cubed interaction is, it is positive mass dimension, so it doesn't generate any quartic. It logarithmically generates a mass term. You could worry about that, but it doesn't generate any.
Okay.
And you can think about the theory in 6 dimensions if you like, where the coupling is dimensionless. Although, as I stressed, this is really a story for the integrand in any number of dimensions. So that's the sort of dumber answer to your question, is that we're not integrating anything yet. We're like talking about the sort of structure, purely rational functions that are seen as the integrand of these amplitudes. It's a very deep question. If I just back up, I think broadly what we've been seeing in this whole story for the past 10 years is that there's a very rich singularity structure at long distances in field theory scattering amplitudes. So factorization, soft limits, and so on. There's a very rich structure associated with these long distance factorizations, and the surprise is that that structure is geometric. It can be captured by these positive geometries. There's a universal aspect of that factorization, which is just what we see in these cubic theories. Every theory in the world has the long distance factorizations associated with these cubic diagrams, and that's what's captured by these associahedra and generalized associahedra and perhaps clusterhedra. In Yang-Mills theory specifically, on top of these universal factorizations, we also have soft singularities, which are not there for generic cubic theories. And the kind of universal long distance geometry that captures also soft singularities is the story of the positive grassmannian and the amplituhedra. So that's there you have to go to more sophisticated, simpler somehow, but more sophisticated in other ways, geometries to capture that. So you can really think about everything that we've been talking about as reflecting some interesting non-trivial structure associated with long distance factorization. There's a whole other thing that we should care about, which is the story of the ultraviolet and the fact that leading logarithms, when we integrate, can be resummed by the renormalization group and the whole Wilsonian picture of things and so on. That is something which is, I think, is the kind of the biggest open problem in this general way of thinking about things. How can we understand the physics of the renormalization group from these sort of more on-shell, more geometric combinatorial ideas? And here, the challenge is mightier than it is with amplitudes, because as far as we know, the best way of thinking about that physics given to us by Wilson is deeply off-shell, deeply Euclidean. And so there's quite a distance from that best way of thinking about it compared to the way that we have now. All I'll say about this is that there is an alternate way of thinking about renormalizability and the renormalization group, etc., via the sort of Kahn-Kreimer Hupf algebra structure associated with the RG, and that has some vague similarities to the kind of factorization pictures that we see for amplitudes. But so just coming back to your question, I think it's a very deep question how to think about the physics of the ultraviolet in this geometric way, but it doesn't obstruct any of the things that we're talking about at the level of the integrand. Similarly with infrared divergences, by the way. You know, if we have free Yang-Mills theory, we get infrared divergences when we integrate, but at the level of the integrand, these are all perfectly reasonable rational functions. And we've been focusing on theories where the long distance factorizations suffice to completely determine it. So somehow, it's not obvious ahead of time, but n equals 4 super Yang-Mills is totally determined by what happens at long distances, its long distance factorizations. This bi-adjoint theory is completely determined by what happens with its long distance factorizations. And those are the geometries that we understand. Trying to continue to the theory of the ultraviolet is a big, open, wonderful problem.
All right.
Thanks. Next, Marco.
Hi, thank you for the amazing talk. I think that my question, I think you may have already just answered my question, but I'm not sure, so let me ask it anyway. I think, so what I was wondering is this factorization structure that you've been studying and discovering, does it respect the perturbation series? Like, does it, so it doesn't combine kind of different scales in terms of the perturbation theory?
Absolutely, absolutely, yes. So
that means that it doesn't.
Yeah, that's a continual and completely reasonable, by the way, criticism of the whole approach is it's still very perturbative. That absolutely. So but that's kind of the point. But let me, perhaps if you don't mind, let me say this point invariantly again, because you know, there's so many other explorations in quantum field theory where people do non-perturbative things, all these spectacular things.
Yes.
Why the heck do we care about doing this lousy thing in a perturbation theory? And the answer is that all the aspects of field theory that we understand non-perturbatively so beautifully are Euclidean. And there's something kind of deep about time and dynamics. And the fact that we do not know, as I said in the middle of the talk, we do not know, embarrassingly, we do not know in the year 2020, we know all the rules for, you know, Euclidean conformal field theory. You hand me a bunch of 4-point functions from a Euclidean conformal field theory, I know exactly what I'm supposed to check to see if it's right or wrong. You hand me a bunch of amplitudes for photons and electrons from formulas and say check if they're right or wrong. I don't know exactly how to check if they're right or wrong. In other words, we don't even know in perturbation theory, never mind non-perturbatively, we don't even know in perturbation theory what the rules are that encode the consistency of causal unitary evolution. Actually, unitarity is easy to check. Even Lorentz invariance is easy to check. The difficult thing is somehow how causality is imprinted on these observables that are measured at infinity. That was the famous failure of the S-matrix program in the 1960s. They thought they could derive from the top down, somehow slavishly derive responsibly what the analytic structure of amplitudes has to be to respect causality, and they failed. And today we know there's many good reasons for why they failed, but it's clear that if this is going to succeed, you have to be much more adventurous and invert the question. We're not going to slavishly derive from the top down what the rules of analyticity, what the rules of causality mean at the level of the amplitudes. We have to see them as outputs, guess some new mathematical structures and see them as outputs instead. That's the sense in which our attitude today is opposite to the attitude of the 60s. But because of our understanding, our ab initio understanding of these things are so poor, we don't even know the answer in perturbation theory. And that's why everything that's being done so far, there's some beginnings of forays into non-perturbative questions. For example, in planar theories, there's some sort of beautiful indications that there's a certain kind of finiteness to how complicated the analytic structure can get. even non-perturbatively. So there are some sort of forays into understanding non-perturbative physics, but it's very primitive. And
but from
it just
the
reflects
point
the
of view
difficulty of the problem. Yeah.
But in the way that you're looking at these geometric structures that occur
right.
in the analysis of the perturbation terms.
That's right.
You know, in order for two different perturbation scales to be related, what would you imagine? Would you imagine that certain cluster systems would be intimately related?
No, there are lots of relations like that. Like, for example, let me give you a very simple one. Because you see the analytic I told you that the singularity structure of these sort of rational functions, of these rational forms, encodes locality and unitary, at least at the level of this integrand. So how does that look? For instance, we saw it already at tree level, right? At tree level, you're supposed to just have flat out factorization. The product that you sit on a pole and you get flat out factorization. At one loop, it's more interesting. At one loop, you're supposed to get, actually, do you mind, Tudor, do you mind if can I keep sharing my, I think it'll be easier if I draw something, if that's okay?
You're already sharing.
Okay, I'm already sharing. All right, so let me, maybe I should,
If you want to share your tablet, you should stop sharing your.
Yeah. So here, I'm doing this. All right, let me just do this. Okay, can you see this now?
Yes.
You okay? All right. So at tree level, we have what we just talked about, right? So we can have something like this, and this is supposed to, we're supposed to have a factorization of something that looks like that. Now, at loop level, let's say you have a one loop diagram. We have one loop diagram. We can have a diagram that looks like this at one loop. We can also have a diagram that looks like that at one loop. And from these, you see different kinds of factorization. For instance, from this guy, you have a factorization. I'll write it suggestively as boundary. You have a boundary of one loop equals one loop on one side and tree on the other. So that's one kind of singularity you can have. But from this, you have a different one. You have the boundary. It can have one where you cut this internal line. And what you get is something that looks like a tree process with two extra particles in it. Okay, so you have something that looks like that. So in other words, if I say this, if I say it loosely, already this physics of locality and unitarity on trees is the boundary of tree. Tree is tree times tree. But boundary of loop is loop. I mean, if I have a general L loop, it has a piece that has L1 loops here and L2 loops here, where L1 plus L2 equals L, and also a piece that has L minus 1 loops, but two extra guys coming out of it, which kind of got identified with each other. Okay, so this is the sense in which properties of these rational functions definitely mix up different orders in perturbation theory with each other. They have to do that in order to reflect locality and the unitarity. And but these sort of qualitative facts about what the factorization looks like are beautifully encoded in the Dinkin diagrams, for example, for these cluster algebras. For instance, it's very natural that the boundary structure, the boundary structure, for example, of the polytopes associated with any one of these Dinkin diagrams is just given by deleting one of the internal nodes. So for AN, you learn that the boundary of AN is what you can get just by deleting one of the nodes. So that gives you just two other chains. So that's why we get that the boundary of AN is some AN1 cross AN2. However, for the type D guys, the boundary structure is a little different, because if I have this, then I can one thing I can do is remove one of these nodes over here. Let's say remove that one. So then I'll get an A cross. I get an A cross a D. So that's exactly what we saw as sort of tree on one side and one loop on the other side. But something else that you can get is you remove one of these nodes and you just get another A. Okay, so you can get plus another A, which is the tree again, which was exactly the two kinds of singularities that we talked about. something with a loop on one side, and something where you open up one of the internal lines to make a tree on the other side. Okay, so definitely different orders of perturbation theory are mixed up. This is also very natural at the level of the surfaces. So if you have triangulations of a surface, then you induce triangulations of simpler surfaces by cutting along some of the arcs that define the surface. And the consistency of the cutting is exactly the sort of physics of factorization.
I have a quick comment and a question. So these delta variables, I'm sure you know this, appeared in work on n=2 theories and surfaces.
Yeah,
in particular in Gaioto-Moore-Knightsky and Fenchel-Nielsen coordinates and so on.
Yeah, I mean, if I had longer, I would love to. There's lots of clear speculations, but they're only speculation. I would love to know. This cluster structure is shown up in several closely related places, and I'd love to know why it's showing up. If it's more than a coincidence, I suspect it's more than a coincidence. But to understand precisely what the connections are. But you see, in the other story, there is no natural reason to stop, right? You can keep on going forever because you get, for example, dions of arbitrary charge, right? Here the sort of deltas are being used for a different purpose. That this is, if I make a sort of speculative comment, you see, we can keep some finite number of these winding sectors and stop. Let's say we can keep one of them or two of them or three of them, take however many that we want, and then stop and then cap off the whole space with these deltas. If you ask in the end, how do you connect this to an amplitude? Remember, in the amplitude, we don't see these winding numbers. So what's natural to do is to take all of the variables that differ by winding and just make them all equal to each other at the level of this thing that we get after we pull back the form to the space. If we do that, let's say we have W of the winding variables, then we have a part of the amplitude which has this big W in front of it, so it has a big part of the amplitude, and that just includes the ordinary Feynman diagram and nothing else. And then there's a subleading part that involves deltas. That's sort of subleading relative to the ones that we kept by 1 over W. But you also can't get rid of it. There's no natural way of sort of getting rid of the W. So that's the qualitative sense in which delta looks like the inevitability of gravity in open string theory. When you look at double trace things in open string theory, whether you like it or not, you get this closed string pull. Here, we're trying to compute, and that's where we first saw the delta. We're trying to compute the double trace cluster polytopes, and we can't do it without having this extra delta along for the ride. But we have this parameter that allows us to control how important delta is relative to the other things, which is the number of winding sectors we keep. So indeed, I mean, it's an extremely natural variable, a set of variables on the surface. It's shown up elsewhere, of course, but we're using it for a different purpose in this story.
Yeah, for sure. The other unrelated question that maybe I should have asked back at the beginning, in this phi cube theory, I think you're assuming you have anti-symmetric structure constants.
Yeah, the FABCs are just they're just FABCs for UN, let's say.
So how far away is this from textbook phi cube theory, where you have a single phi or phi to the 4?
Excellent question. So let me give you a technical. I'll give you a technical answer at tree level, but I think this butts up against a very deep issue so let me say both things if you don't mind. Just at the dumbest technical level, let's say you want the amplitudes for the totally uncolored textbook phi cube theory of the single phi. Okay. Mm-hmm. At least at tree level, I hadn't thought about it beyond tree level, but at least at tree level, there's a trivial way of getting it from these ordered amplitudes that we talked about. The dumbest way you could, just sum over all the orderings. If you sum over all the orderings, you can easily convince yourself that you just get every phi cube diagram the same number of times. So up to some overall n factorial or something, it's exactly the amplitudes that you get for the uncolored single phi theory. Okay, so there's a relatively simple way to get the tree amplitudes for the single real phi cube theory from the ones that we're talking I suspect it'll be more complicated at loop level. I haven't thought about it. The deeper issue is the following, and it has everything to do with, this issue shows up many places. It has to do with that all of the kind of geometric structures related to, the obvious geometric structures related to amplitudes are about colored things with some ordering in them. And there's and uncolored things, so like Yang-Mills roughly, and uncolored things like gravity roughly, always end up being best thought of, at least in this way of thinking about things, as the square of Yang-Mills. So this is true in string theory, for example, and it's true in these more recent examples as well. And the fundamental reason for it is very basic. Let's think about what a sort of geometry could possibly look like for just single phi cube theory. What is the amplitude? The amplitude is 1 over s plus 1 over t plus 1 over u. There's only one pole, so if there's any geometry associated with it, it should be one-dimensional. But there's no sort of, obviously, there's no one-dimensional geometry that has 3 boundaries. And yet we have to have these 3 boundaries with s, t, and u. This is related to the fact, for example, in string theory, if you look at if you try to understand the singularities of amplitudes as going to boundaries, the first singularities are codimension 1 only for open strings. For closed strings, they're codimension 2. They're real codimension 2. So if you have like 4 points on the sphere, it's a real codimension 2 boundary that gets the long thin tube connecting the guys with the points separated on 2 sides. So it skips this first real dimension 1. That's the difficulty that for genuinely uncolored permutation invariant closed string, all these equivalent things, we have the basic difficulty already at 4 points of trying to tie the amplitudes to some to try the singularity structure of amplitudes to the boundary structure of some corresponding space. It's natural to do it for colored things. We don't yet know how to naturally do it for uncolored things, and I think that's one of the other sort of zeroth order conceptual problems in this business. Of course, you can square Yang-Mills in a million ways, but I personally think that's a defect. It's not. I mean, it's a way of doing it, but gravity amplitudes, closely amplitude have properties that are obscured by writing it like that. There should be more intrinsic way of thinking about what they are, and we're still missing it.
Thanks. We'll take 2 final questions. T. Das.
Hi. I had a very naive question way back at the start of your slides, where you first described this, the polygons and then the form, with the logarithmic singularities.
Yes.
So this might be very naive, but could you say something about the role of convexity in that very basic setting? Because if the polygon or the polytope, okay, thank you.
Yeah. So the word positive in positive geometries is really that that any notion of interior, the easiest notions of interior involve the notion of positivity. If you want to talk about points on the inside of a triangle, then you think about the points on the inside of the triangle as the weighted sum of the vertices with positive weights. And so in those simple examples, it's also naturally associated with the notion of convexity, the sort of convex hull of a bunch of points. Having said that, in the entire story of positive geometries and polytopes, everything is convex, and that's it. The story of the amplituhedron, which I didn't talk about at all, is sort of 1 or 2 levels more deeper than everything I've been talking about today. And it involves several generalizations of these ideas of positivity and convexity away from affine spaces and projective spaces into grassmannians and beyond. In some sense, it's generalizing the notion of convexity, but in many examples, when you can sort of map it dually to some to sort of flat polytopal looking problems, you get non-convex things, which are nonetheless positive from this other point of view. So, so I would say that there was some kind of notion of positivity, some kind of notion of convexity, but it's not always the one that we're most familiar with. But that's really seen in this other story of amplituhedra and n=4 super Yang mills. As I said at the start, it's a little ironic that we ran into these structures first in the setting where at least some of the mathematical ideas involved were more unfamiliar. So involving generalizations of polytopes into grassmannians and so on and so forth. But the whole story of just these simpler phi cube theories is just associated with flat out polytopes. And then it's all convex in the way that you're used to.
Great, thank you. Thanks.
And last question from Azadeh.
Hi, thank you for the nice talk. You mentioned that delta has a nature similar to gravity, which by the way is very charming, but I'm wondering how much of it is related to this bi-adjoint structure of this specific phi cube theory.
Well, I don't know. I mean, as I said, this is at the moment it is just it's a vague analogy. There are aspects of it that you can start trying to study more sharply, but really at the moment it's just a vague analogy. It sort of shows up in the same place, we're used to it showing up when we go from open to closed strings at one loop level, and it has the same kind of function. It sort of universally couples different sectors together that otherwise are disconnected. And if they were disconnected, you couldn't close up the whole space to make a clusterhedra. So they're sort of, it's crucially there to talk to everybody universally. So yeah, it's way too premature to say. I mean, we have to see more whether even at the level of the geometry and the combinatorics, it looks like gravity. That involves really understanding what happens on these facets. And by the way, when we go beyond these simplest examples, we don't just have one delta, we have many deltas. So we have to interpret what those many deltas would mean gravitationally. But there's something you can do, which is to sit on the poles involving delta, or sit on the facets involving delta. And if it's vaguely gravitational, then on those facets you should see factorization into lower things, which are then sort of universally coupled to each other. So for instance, if I take this example with this annulus at one loop, sitting on the delta facet, you really see that you get the product of the sort of gluon amplitude, sort of single trace on one side, multiplied by what you get from the outer annulus, multiplied by what you get from the inner annulus. That structure is just what you'd expect from the exchange of a tree-level graviton. But there's a lot left to be understood about how to interpret the multi-deltas and really what the whole clusterhedron structure looks like in general before we can answer that question in more detail.
Thank you.
There is something to check. I mean, there is something internal to this story to check to see whether it even has a prayer. Yeah.
We're basically out of time. I just wanted to thank you again for the wonderful talk and discussion. And yes, we can have another round of applause.
All right.
And yeah, thank you so much for joining us.
My great pleasure. Thank you.
Yeah, and we'll see you and everyone else in a week.